Can you do that even if you have a certificate?
Few administrative announcements. So I had emailed you already. There will be no class next week, so Thanksgiving. So yeah, you can enjoy and you can have a great Thanksgiving full week. And one more thing is, initially when we planned this, we were planning to release the project next Thursday, which happens to be Thanksgiving Day. So we will not be releasing it on that day. So we will be releasing it on the next Monday. After Thanksgiving, the Monday after Thanksgiving, we will be releasing the project 5, and we will be having a discussion of the project on the next immediately on the next day, this Tuesday.
Would you still be working on it, or you're not releasing it to not like pressure us or whatever?
Pardon?
Would it be ready to go then?
Yeah, it would be ready to go then. Not very sure. Mostly it will be ready.
I was wondering if it could still be released Thursday. Well,
So anyways, we are going to like extend the due date. It's
Okay.
not going to be the same.
okay.
We just thought like we don't want you to be working on operating systems during the break. But if you guys, okay, maybe I'll just take like a vote. If you think, if you are like really interested, so how many of you like want to be released? I feel bad. Yeah.
Is the midterm or is the final on December 15th? Or when's the final?
I think it's on some.
Because I don't really want a project due the same day as the final, because then I won't study for the final.
So it will not be due on the same day. It will be due the next week after the final. I mean, yeah, sometime like 20 or something like that. So you'll get actually more days.
When did the grades get submitted?
Should
We
be.
get our, when's like the semester officially end?
I'm not very sure of the exact date, but at least at the university, it's the next week. We have an exam on Friday, but in the university, it's actually the next week, which is the exam week, which is like from 17th or something like that. So you have the whole week.
While we're on the topic of final exam, is it also going to be shifted to now be from 7:30 to 9:30, which was the original schedule time?
Yeah, so it's going to be shifted. So the final exam will be from 5:30 to 7:30 as we had the midterm, but it's on the same day. December 15th, I'll update it in the website, but it's going to be from 5:30 to 7:30. Okay, and the original time was like 7:25 to 9:25 or something like that. But that will be updated, yeah.
You said the project will not be due December 12th.
The project will not be due on December 12th. Any questions? We will have a worksheet due, I think. So one more thing about the worksheet is like, I think we will have a worksheet due for next week because the topic that we are going to cover today is like really important, which is the file system. And so I think it would really help you guys if you do a worksheet. And initially we just had like, we'll be dropping the lowest score of just one worksheet. But I think currently we've decided to drop like 3 lowest grades of the worksheets. So again, we are not very sure like how many worksheets we are going to have. Maybe 13, around 13. If there are around 13 worksheets, then like irrespective of the number of worksheets we are having in total, the lowest 3 grades will be dropped.
So will we just email the worksheet in, or will it just be?
Yeah, like for next week, everyone just like email the worksheet to send me. Any other questions? What? Yeah, I think that should be fine. Yeah. Okay. So if you want, like, we'll make sure that if you want, like, you can just have like 2 weeks for this particular worksheet and just turn it in like the week after Thanksgiving. So if you have any travel plans, you need not worry about this worksheet for next week. Okay.
ever gonna get up on her, you know, when we said, like, I only have 5 machines on the thing I could have gotten more access from.
I'll talk with the TA.
Yeah,
Yeah.
just send me those photos.
Sure, yeah, I'll just talk with the TA. Just make sure like it gets updated pretty soon. Any other questions? We got any questions? Let's start by like reviewing whatever we saw in last class. We started the third part of this course, called persistence, and we started by looking at high-level structure of I/O devices. If you remember, like each I/O device has two parts: the interface and the implementation. Then we even saw like a canonical device and even like a simple protocol about how the operating system communicates with the I/O devices. And then we went into, we started like looking at a very specific device called the disk, hard disk. And initially we saw the structure. We have like a platter, and the disk has multiple tracks in it. And the disk has a disk head. This is the disk head. Each track has like different sectors, like say 0, 1, 2, and so on. And other things that we saw here, this part is called the spindle, and we calculated what is the difference between sequential read and random reads on a disk. And even if you don't remember anything from last class, at least I think you should remember like the sequential read, like the performance or okay, let's assume the time. If you're asking the time it takes to for sequential read compared to the time it takes for random read, or maybe it's like the rate would be more appropriate. The rate of for sequential read when compared to the rate of the random read operations, the rate of sequential read is much higher compared to random reads, and this is an important thing that we will be like coming back to for most of the class. And then, after working out these calculations, we started looking at disk scheduling. Remember, the first thing that we saw was like the first in, first out scheduling, where the disk services the request just in the order that the requests come in. Then we saw something like shortest seek time first, and in this scheduling policy, we make sure that if multiple requests are on the same track, we first service those requests before switching tracks. So the main purpose here was just to like make sure that we don't spend time seeking. And the problem with the shortest scheduling time first was, shortest seek time, this stands for seek, shortest seek time first was that since we are only focusing on the seek time, if there are like new requests that are coming in to the position, for example, let's assume if the disk is at this innermost track, and if there are requests that are coming in, like a lot of requests to the same track, then the requests that are pending on other tracks will be starving. Like these requests will be starving because the disk's head will not even move from the innermost track to any other track. Okay? And this starvation was one of the problems here. So one problem here was starvation. And the other problem that we had with the shortest seek time first was, you remember? Anyone remember what was the other problem? The other problem was just like it did not, the shortest seek time first only focuses on the seek time. It completely ignores the rotation time. And so it ignores rotation. And so we came up with another scheduling policy called shortest positioning time first, or it's also called shortest access time first, which takes into account both the seek. This takes into account both the seek and the rotation times and compares the two and makes decisions based on that. If let's say in a particular disk, if the rotation is like slower than a seek, then it works accordingly, in the sense it prefers to seek instead of waiting for a complete rotation, things like that. And so here the problem with this was again, so here using this we are able to resolve the problem of rotation, but still starvation might occur in this case, and for that we had like a lot of options. The different algorithms that we saw were like bounded, shortest access time first, and this was the idea with the windows. If you remember, we had like multiple window sizes. We had like a window size of 2 or window size of 3, and we were saying like before we complete before we proceed to future requests, we should first schedule the requests that are in that particular window. And I realized that there was a bug in the simulation, the last simulation that I showed, where I think Stephen pointed out that it may starve, like the starvation may still be possible in the window. I will be showing the simulation again. There was a bug, so I will show you what happens there. But before looking at that, the other things that we just saw were the scan algorithms or elevator algorithm. And in the scan, we actually saw like different variants like C-scan or circular scan, which makes sure that all the three tracks are, the requests on all the tracks, all the end tracks are treated equally, and the middle tracks are not given more priority, because we saw like in the scan, the order of operations would be just like 1, 2, 3, 2, 1, 2, 3, goes on this way. And so if you see 2, the innermost track, there are only 3 tracks, the requests in 2 will be serviced very frequently when compared to 1 and 3. And so in C-scan, the order will be just like 1, 2, 3, 1, 2, 3, 1, 2, 3 in the same way. And then we also saw another version of the scan algorithm called the freeze scan, where we maintain 2 separate lists or queues, Q1 and Q2, and whenever requests are coming in, initially we just fill one particular queue, and once that queue is full, we freeze that queue in a way like we don't add any more requests to that queue, but instead the future requests would be added to Q2, and and the other way around, in the sense once Q2 is full, Q2 would be freezed and the requests would be serviced, and then we will be like accessing the requests, and then we will be adding the new requests to Q1.
Something that wasn't clear on for number 3, we're always calculating the one that's nearest, right? So we're looking at anything that's pending, going to the one that's nearest, and then doing calculation again for the remaining. Okay.
Exactly. So for the third one, we are like from all the remaining requests, we are just checking which one has the shortest access time. It can be a combination of seek and rotation.
We're never doing a path, we're just doing between 2 different axes. So that
So if let's assume there are like 10 requests that are pending, we are out of those 10, we are checking which one is the nearest from wherever the disk head is currently positioned.
And once we get to that, we're doing the remaining 80.
Exactly. So it is basically a greedy algorithm. It takes the entire thing and just checks like at this time from this position, out of the remaining requests, which is the nearest one to act, like which has the shortest access time, and just accesses that. And then in the remaining thing, it calculates it again. Any questions about this, about the review that we saw? Okay. So, the problem was, okay, so we ran the simulation. I think this was the last simulation. If you notice here, so there was a problem here. So 12 was in the window size of 3. 12 was within the window size of 3. Like when we were considering the 3 requests, 6, 12 and 8, it was in the window size. But we just skipped 12 and we were actually, we serviced 8 and then we will be servicing 11, 14 and then finally we will be coming to 12. So the question that was asked was like, if this is the case, if we keep adding elements to the window size of 3 before all the elements in the window are serviced, then wouldn't this cause starvation? This actually would cause starvation, but this is not the correct simulation for how the window sizes work. So for example, the problem was just with this script, we had we had just the shortest access time first here, but this should be bounded shortest access time first. If we just make this modification, now we can see first services 20, then 18. The window size of 3 is fixed right now, 18. Then after finishing all the 3 requests, only then the window size. Now the window has 6, 12 and 18. So 6, then 8, and then we service 12. This is what should happen. Okay. And finally we go and service 7, 14 and 11. Okay, so since this is the correct way that the bounded shortest access time first works with Windows, there will be no starvation because we make sure that those elements in the window will be serviced before we add new elements to the window. So let's assume in a similar way, if we have window size of 4, or if we just keep on increasing this particular window size, then do you think would it be better with respect to the total time that we have? Do you think it's going to be better? So now we have a window size of 4. Yeah, this has that issue. worked correctly. Let's check. So we access 20, then 18. We go to 10. Yeah, so we are waiting for 12 because that is now in the window phase of 4. So till we access 12, we will not be accessing the other elements. Now finally 14 is accessed. So the question is, if we keep on increasing this window size, let's say if we include all the elements that we have currently, that all the requests that we have received, do you think it's better? Because with Windows, what is happening is we are restricted to select the requests only within that window. So what if all the requests that the disk has received is in the window? Then do you think this is going to be better? Let's just check this. So now it can just use the entire information. It can check So definitely the total time was less than whatever we had for window size of 3. If we check window size of 3, at 1245 as the total time, and now we had only 735. So do you think it's always better to have, so is the best scheduling policy like bounded shortest access time first with Windows? With the window as the entire size?
But if the windows the entire size, then does that just reintroduce whatever starvation problem we were trying to avoid in the first place? Because this is the reason you introduce the windows, to make sure that like one request doesn't get pushed off.
Okay, so yeah, I understand that, but the idea here is, okay, if we have the entire window size, if we're considering all the requests that we have at that time, then this is again going to introduce a starvation problem, because each and every time it's going to consider the remaining requests that we have and just pick the one that is the shortest to access. I think then the question is, if the window size is larger, like let's assume not everything, but if it is larger than 3, let's assume 10, okay, window size of 10, then do you think would it be better than having just window size of 3?
Couldn't the turnaround time suffer?
Turnaround time? What do you mean?
Like, let's say you're the first one or the second person to enter your request, but you don't get served until the 10th slot just because of your position.
Yeah.
Whereas if it's a window size of 3, you're guaranteed to get it within three attempts.
Yeah, so the time that disk requests comes in, and when we compare it to the time that it actually is scheduled, I think that will increase definitely when we increase the window size. That is a problem here. But more than that, but along with that, maybe I'll show you like next one. So the thing that I'm trying to is. This is whatever we have here is a greedy algorithm, because it computes just the immediate next best request to service. So I'll just show you one more, the last 2 simulations here. So let's assume we have these 5 requests, okay? So in this particular simulation, at each and every after or like before choosing each and every block, the blocks that we have are 9 to 17, 29 and 6. What happens here is, since it just decides what it wants to schedule, looking at this entire list, it may not be the optimal scheduling decisions, because it takes the entire remaining disk, like the blocks, and it just like schedules, okay, at this time, among these things, 9 is the best thing, and then 2 is the best thing, and 17, and it goes on like this. And so this gave us a total time of 1095. But the same thing, if we can do something like this, these are same requests again. But this does not do it in a greedy way. It spends some time initially to access the first requests, but it is benefited by doing so by accessing 17 as the first sector, so as the first block, and this was 1095, and this was like slightly better. If you see here, this was the total access time was 1065. So if we do a greedy scheduling like we saw, then it just means that at each and every time we are making a decision based on the current request that we have, and so we just don't want to waste time while servicing that particular request, and so at the end we may end up wasting a lot of time, as you saw in this particular example. So the idea here is we really don't have just like one way that we can schedule these things. There are a lot of ways that we can schedule the same list of blocks in, and this was like one optimal way that we just showed.
What was the first one again? Can you just go back a little bit? So is the idea that in this optimal one, it chose to pick one that was a little farther because then that puts it in a position that the other ones are closer than they would have been previously, so it's kind of like a shortest path kind of or whatever.
Exactly. So here in this case, it shows that okay, when the disk started, okay, 9 was the best thing to choose, but in this optimal, it didn't choose 9 as the first block, but instead it chose 17. Because it did so, at the end, it was able to like, if you see here, initially this did not do any seek, and that was the reason it chose like 9 and 2. But if you see here, initially we did some seeks, but we were able to like reduce the seek and the rotation times at some later point in time, using which the total time that we take to access these blocks is reduced.
Can you do the second option if you don't have all of the requests at the beginning though? With the second option, you have to have all of the requests, right?
Yeah, in the second option, we have to have all the requests at the beginning, I think, but even in this first option, we are assuming that we have received all these requests.
Oh, that's true.
Okay. Because using that, we are picking the best possible.
But you just pick one of the best.
One of the best, yeah. The best, basically, yeah. So this just shows that there is no like one right way. There can be a lot of schedules that are possible, and many of them would be like decent schedules, but some may not be like as good as these things. Any questions about this? The last thing that we like to see in this scheduling is like, where do you think the disk scheduler, the code for the disk scheduler would reside? Do you think it would reside in the operating system, or can it reside in the disk itself?
The disk needs to know like how fast it like rotates and all that stuff to calculate like how long it's rotating.
Well, that could be stored on the disk somewhere.
Pardon?
Like information about how fast the disk rotates will be stored on the disk, and the operating system can just look at that. I don't know.
Yeah,
Like
you can look at that. So initially, when disks were like much simpler, we had the scheduler, the disk scheduler, just in the operating system. The disk scheduler was just present in the operating system, and even though the operating system just viewed the disk, if you remember, the operating system just views the disk as an array of blocks. Even though the operating system views the disk as just an array of blocks, we had the disk scheduler just in the operating system, and these algorithms like the shortest seek time first would have, the operating system would have no idea about the different tracks or the different sectors in each track and stuff like that. So the way they approximated those algorithms in the operating system was using something like, if the disk head is currently, if we know that the disk head is currently at some block n, how near is the blocks that we, like what is the nearest block from the list of blocks that we have. So it just did something like that, and it was like only approximate algorithms. At the same time, when disks became more complex, people started writing disk schedulers like here. In the disk itself. So the disk itself can have some code that is used for scheduling the different requests. So currently in most of the systems, how this works is like there are these two schedulers that are present, and the operating system picks a list of blocks that it's things like, okay, these are the things. This is my schedule, it gives it to the disk, and then the disk just picks from that particular list that the operating system gives. The disk later picks the best thing that it wants to schedule. So the final decision is made by the scheduler that we have on the disks, because it has like more like accurate information about like how many sectors are there, how many like tracks are there on the disk, where is the disk head currently positioned, and all the information is present here. One more thing to discuss here is the disk. Let's assume the platter that we're talking about was like here. The actual, if the disks, the platter, the tracks, and if everything was here, we have something called a disk, like a cache. We have a cache on the disks. The way this cache is used is if someone does a write, let's assume a file is being returned to this disk. We write this file. The write initially just happens here. This file is just returned to this cache. And after a few seconds, the disk actually takes this file from this cache and writes it to the platter, to its actual location on the disk. And so if there is a crash in between the time that the contents of this file goes from this cache of the disk to the actual platter where it will be persistent, then that file's update is gone. Okay? The file's update will not be seen on the disk when the system reboots. We'll be learning more about this in today's class. Just wanted to give you an idea that we have something called a disk cache. And so usually whenever we write something, the write just happens to the cache. And only then it actually gets persisted on the disk. Okay. The idea for today's class, we are going to look at with this, we are completing this scheduling, and then we are moving to file system. So we are going to start with the file system APIs. What are the different APIs that the file system provides? And then we are going to discuss file system implementation. Here we will be discussing two things. Like one is going to be the data structures in the file system, and we also have the access methods. This is the high-level idea for today's class. Let's start with the file system APIs. And if you remember the organization, we have the application layer, and then we have a file system layer. Okay? And below the file system layer, we have something called the block IO layer, and then we have device drivers. And then we have the actual devices. Okay? And now we are going to focus on this particular layer called the file system layer. So we are going to see like what are the different APIs the file system provides. Most of this we would already know, but we will be looking at like one more level of detail, like not just at the command level and the system call level, but we'll also be looking at what happens internally when we create a file or when we remove a file, what are the different system calls that are actually used. So for example, if you remember, the APIs that the file system exposes are like open or create, both are used for creating new files. Then we have read, then write, close. These are things that we already know. But along with these things, we will be also looking at a few other APIs that the file system provides. And in the second half of the class, we will be looking at okay, how is this file system actually implemented, in the sense how do we actually store the files and the directories on like the disk, on the hard disk, so that we can retrieve them when we need them later. So the file system provides two basic abstractions. First abstraction is called a file, and second abstraction is called a directory. This file, we also call it as a regular file. So this regular file is nothing but an array of bytes. This is just an array of bytes. And it also has something called a low-level name. And as we know, it also has a human-readable name to identify it uniquely. So you may think like a file is just like an array of bytes. okay, with the human readable name, which we can actually understand, and we also have something called a low-level name, which we will be looking at in more detail. And the low-level name is actually a number, and it's called an inode number. Low-level name is just called an inode number, and each file has a unique low-level name or a unique inode number. So the directory is like a special type of file. The directory is a special type of file, and it also contains like a human readable name, and a low level name. You can think of a directory as the contents of a directory to be like array of records. Usually the structure of a directory just looks like this. The human readable name and the low level name. Actually, the directory is just a mapping between a human readable name. It has an array of records of the human readable name and the low level name. So here by human readable name, let's assume if this directories, the contents of the directories are just files and other directories. So directories can contain files and other directories within it. And let's assume if there is a file called a.txt in a directory. So the contents of this particular directory would be a mapping from that human readable name to that low level name. So low level name can be like, it's just a number. This is like the inode number. This is the inode number that is corresponding to this particular a.txt file. And if there is another directory called directory 1, which is inside this particular directory, then it will also have a corresponding low level name inside this. So these are just the high level abstractions that the file system provides, the files and the directories. So first let's start with the files. So the first operation that we are going to see is the creation. So even if we use, there are two APIs for creating files, like open and create. These two APIs internally, the system call that will be called is called a create system call, which we are going to see right now. So in this simple file called create.c, all we are doing is calling like create with this file 1, okay, and we are like setting some permissions with this particular file, and then we are just checking if the return code that this file returns, if it is greater than or equal to 0, then we just proceed. And the same thing can be replaced with this call to open file, and o underscore create is just the option given to, okay, we're creating this file, and then we have the permissions sitting here. So we can just see, like before we did not have file 1, now we just have file 1, and file 1 currently has no data. We can just check using cat. So file 1 currently does not have any data. Okay? But the thing that we would like to see is, let's maybe just remove file 1. Okay? And while running this create, let's trace all the system calls. We are going to trace all the system calls that this function generates in the background. Okay? So this program, so here I'm just saying strace. I'm placing the output from this particular command in a file called dump, and I'm running this particular program dot call create. Okay. So strace is a command that is used to trace all the system calls that this particular program generates in the background, and the output of that particular trace is stored in this file called dump. Now when I open dump, we can see here that like it's calling exec v the break system call for expanding the heap, and it's doing a lot of things, but the main thing that we are interested here is this particular line where it says that create file 1. The final system call is to create a file at line 24, create a file with the name called file 1 and with this particular mode, in this particular mode. That's all it's doing. And what is this 3? So the values that we have on the right hand side here are the return value from this particular system call. So the 3 that we have here is just whatever this particular system call returned. So in this case, the system call has returned a value of 3, which is nothing but the file descriptor. Remember, this is just the file descriptor for this particular file. So the reason why it is giving 3 is by default, all processes have like 3 standard descriptors, 0, 1 and 2. 0 is for standard input, 1 for standard output, and 2 for standard error. And so the next available descriptor is 3, and that is the reason it has given this descriptor 3. So here, one thing that we would from whenever a process, so let's assume in the operating system, whenever a process opens a file, okay, whenever a process opens a file, it has something called a file table. File table, which is nothing but like these descriptors 0, 1, 2, 3. So initially this was pointing to standard in, and this descriptor is pointing to standard out, and 2 is pointing to the standard error. And now we got this descriptor. This descriptor is actually pointing to the corresponding file called file 1. This is pointing to this corresponding file called file 1. Okay. And along with these, okay, these are called file descriptors. These are file descriptors. Along with these file descriptors, for each and every open file that this process is accessing, so for example, let's assume there is one more file descriptor 4, and it's called file 2. Okay. For each and every file that this process is accessing, the operating system maintains something called the current offset. Current offset. So what this means is, when, let's assume if this is a file, assume if this is a file F, okay, with the file descriptor 3, then if we are going to, let's say, read this particular file, initially the current offset would be at byte 0, and let's assume maybe like reading, there will be like a reading offset and a writing offset. So if we have opened this file for writing, that will be this right offset pointing to 0, which is the first initial position in the file, or if we are reading, it will be the same. Let's assume there are some contents here already in this file. If there are these 5 characters, then it will be pointing here, and then if we issue a write system call, if this process issues a write system call on this particular file descriptor, let's assume the value of 3, and it says write or read, okay? In this case, since we already have content, let's assume we have read, okay? If we call read system call on this particular file descriptor and say we want to like read 3 bytes from here, then all it's going to do is just like read A, B, and C and increment this offset here. So the offset moves from here to here. So now the current offset would be at the position 3. And so if this process makes one more read, okay, if a process makes one more read, then it is going to actually read from the byte at position the position 3. Okay, so this offset is maintained for each and every file that this particular process has opened. Okay. So let's just do this here. So I'm just opening this file and writing like 5 characters in here. And if you do ls-lrt. So in file 1, we see the number of bytes to be 6. Any idea like why do you think we only wrote like 5 bytes inside that file, but the size it shows it's like 6. Any idea? So So it's not like a null character. So most of the text editors, what they do is like whenever we write some contents in the file, at the end it just adds a new line character. So that if we do like, let's say, cat of that particular file, this new line that is printed, this using that new line character, if you want we can do like a dump. So 41 in hex corresponds to A, 42 in hex corresponds to B, then C, D, then E, and this character 0A, if you look at the ASCII table, okay, this character 0A in hex, which is like 10 in decimal, this corresponds to the new line character. So it just places the text editors, just place these new line characters at the end. That was the reason just we had that extra one byte here. And so, okay, if we have this, okay, now we'll see like a function called so we are talking about these offsets. If there is this file with contents A, B, C, D, and let's say E, and initially if we are here, okay, and if we want to write something to the end of this file, then we will be calling a system called lseek. There is a system call called lseek, and in this system call here you can give the file descriptor. You can say like an lseek of the file descriptor, and then you can tell like where do you want to from where do you want to seek. For example, I think there is an option called seek end. You can say like you can seek from the end. So now it will start from here, okay? It will seek to the end, and then we can maybe write some things here. Okay. You can look at the man pages obviously, but the idea here is just like even without reading or writing any contents from this particular file, we can switch the file offset of that particular file using this system called lseek. This system called, we can seek this thing. We will just look at a sample example. So it says like reposition the read or write file offset, and we have it takes in the file descriptor, then it takes in some offset, and then it takes in some events. Don't worry about this, but here it just says there are like this offset can, so we can seek the offset is set to the size of the file plus offset bytes. So that is, these are three options here for the events, which is like seek end, seek from the current position, and this is like some set offset that we can do. Okay. So in this particular file, we are just opening the file in this particular program. We are just opening the file that we just created, which is file 1 in write only mode, and then we do an lseek. Okay, we're saying like we are going to do an lseek, and the events is given a seek end, which is like starting from the end of the file. Okay, starting from the end of the file, we are going to seek 0 bytes. That's all this says. Starting from the end of the file, we are going to seek 0 bytes. So it just moves the offset to the end of the file. And after that, here we are just adding some, like just a single character called B at the end of the file with the particular \n character. And we write this particular contents from this buffer to this file. And so now this write is not going to start from the beginning of the file, but instead from wherever the current offset is. The current offset currently is at the end of the file. And so it's going to just add this at the end, and then we just print the return count and then see. So these are two things that are returned from that particular thing, but we can now just do a cat of file 1 and see that since we had that new line character here, that was the actual last character that we had, and after that particular byte, the new thing like B was added here with the new line. The question.
So if we had seeked to the end of the file with write insert between the existing characters, would it have right? If we like seek halfway through.
Yeah, it just overwrites from that particular position. If you just seek like halfway through the file, and then if you just start writing, it really does not care like what characters or what content is in that particular position previously. It just starts overwriting that particular place. So now what we can see is how does this cat work? Yeah.
What if we didn't call lseek at all and we just called write? Where would it start writing?
So if we did not call lseek but just started with write, it just starts at file offset 0, because whenever it opens a file, the file offset is initialized to 0, the first byte in that particular file. So it just starts from there. So now let's just see, when we did this cat file 1, what is happening in the background? Like how does, or what are the system calls does this cat program generate? Okay. So again, we're going to use trace, system called trace, and do this command like this. Here we are just running a program called cat with the argument file 1. Now if I open dump, I should be able to see this. Okay. Again, you may like go and look at the other details if you're interested, but the thing that we are interested here is we are so cat opens the file 1. If you see here, okay, cat opens the file 1 in a read-only mode, and then it reads from the file descriptor 3. If you can see here, this 3 just corresponds to the file descriptor number. It reads from the file descriptor 3 for this particular process, and this is the contents that it reads from the file, okay? And what is the third argument to read? It's the size of the buffer. So it is the size of the buffer that it is reading this whole contents into, and immediately it does a write. Why do you think cat is doing a write? Exactly. So it is all it's doing is the write that the cat program is doing is to the file descriptor 1. As we just saw previously, file descriptor 1 corresponds to the standard output, and so it is printing. So this write just prints the contents of that file to the standard output, and these are the number of bytes that are being printed. Okay. Okay. So now, any ideas? Do you have any ideas if we are going to like do a remove of this file? Okay, remove of this file. What system call do you think will be called in the background? Do a remove. Let's maybe just check that and then let's see if it makes sense. Okay. I'm just doing the STRAY system for removing this file. Removing this file. So when we do a remove, okay, the system call that is actually called is called unlink, and unlink cut is just like a different version of the same system call. The system call that we actually use internally for removing a file is called unlink. It may not be like it may not make sense right now. Like what does it mean to unlink a particular file? Okay, but we will just see like what it means. So unlink is a system call, and each file has something called links, okay, which we will be looking at in a few minutes. Let's first again maybe create that file 1 manually. As of now, just remember that when we do a remove, okay, when we do a remove of a file, internally it just calls a system call for unlink. And now let's try renaming this file, and we'll get back to this like later. Okay, what this means we'll get back to it in a few minutes. But now we'll try to do an strace on like the rename command, like the move file 1 to file 2. Here we are renaming the file 1 with the name file 2. So here you can see for the move or the rename command, the internal system call is also just rename, just matches. That is a system call called rename, and so the Unix command or the Linux command are, so the MV just corresponds to this particular system call where we like rename this particular file. And one more interesting detail here is if we have this file with contents, let's assume A, B, and C, and when we are going to write some things to this particular file, okay, when we are going to write, let's say 2 more characters to this particular file, and write takes place, usually there will be like a new file that will be created. You can think of it to be like file.temp. Okay. This file will still be there. There will be like a new file that's created, and we can just add details like D and E. And once these new contents are added to this temporary file, like file.temp, at the end, this file would just be renamed to file. And so this, from the user's perspective, this just seems like, okay, we have added some content to this particular file.
Will it have the same inode number as the original file?
Pardon?
Will it have the same inode low-level name?
Yeah, it will have the same, after adding some contents, it will just copy both the name and the inode number. So now we are going to see how can we look at the different, like the details of a particular file. So in this case, if you want to look at the details of this file 1, like more than, or file 2, we just renamed it. And so if you want to look at this detail, there is a command called stat. So the stat of a particular file gives you these details, and the important things to note here are the name of the file is here, the size of this file is here, and there is something called blocks. This shows the total number of blocks that are needed for this particular file, which we will be looking at in the file system implementation. And then here it says the type of the file. So this file is just a regular file. Okay, this file is a regular file from the perspective of the file system. And then if you see here, there is something called inode. Okay, and this number is that low-level number or the low-level name for this particular file, and this will be unique. And then we have the links. As we just saw when we were doing the remove, we called a system call called unlink, and here it says that this particular file has just one link. Okay, we will see like what it means. Other than that, like not much. The access, modify, change times are here, but these are the details that we get from whenever we want the details of a particular file. So let's just do a stat of a directory. We do make directory 1. So here you can see the number of links is 2. You understand this later, but the important thing here, I just wanted to show this, is just this particular thing. Like the type of this particular file is a directory. In directories are also just like files from the file system perspective. They are like some special type of files from the file system perspective, and it has like a series of records, which is just a mapping from the low-level name, from the human readable name to the low-level name. And even this has like a low-level name, which is this inode number. So the next thing that we are going to see is when we, like the directories. Any questions about files till now? I think it's 6:40. Maybe you can take a break and then we'll continue with directories. RMDIR, and usually this does not work if the directory is not empty, and just to make sure that we are not using it by mistake. Okay? So, and then for reading a directory, we have ls. Okay? Again, one important thing with the directories is the operation write. Okay, so can we, as a user, can we write to a directory directly? So the answer is no. Okay, we cannot write to a directory directly because directories are maintained with the, like a special format by the file system, and so write is not possible. So what we mean here is like the user cannot write some things directly to the directory, but the file system is the only entity that can actually modify the contents of a directory. So currently if directory, let's assume slash who is this directory, this is the directory that we're talking about. So then this is going to have this human name and this inode number or the low level name. So here the contents of a directory usually looks like let's assume this directory foo, if this is a file system hierarchy, slash foo is here, if foo has like a.txt and b.txt, then here we're going to have a.txt and b.txt, and this particular dot just corresponds to the current directory. These are like special directory names. Dot corresponds to the current directory, and double dot corresponds to the parent directory. And if there is a dot, then let's assume there is some inode number 1731. And since this is directly under the root directory, usually root directory has inode number of 2. So the parent's inode number is 2. And let's assume some inode numbers here for A and B. And if you want to access this particular file, either we can access it saying like slash foo slash a.txt. This particular way of accessing this file is called absolute path name. And if you are inside this directory foo, and if you want to directly access a.txt, we can directly type a.txt, and this is called a relative path name. A.txt is called relative path name. Now we are going to see a program called read directory. Okay. It uses a system called open directory. Okay, it opens the current directory dot. It opens this current directory and stores it in a pointer to a directory structure. This dir is a directory structure. It is present inside this thing called directory entry.h inside this header file, and this is a directory pointer to this directory currently, and this is like a struct called directory entry which has the file name, okay, which has the name of the file, then the inode number and like a few other things, but only two things that we are mostly interested in is just the file name and the inode number, okay. And the type of the file is also here. This is again, is it a regular file or a directory? The type is also here. And then we create, so here what this program is trying to do. So it's calling something called read directory on this directory pointer here. And until it's doing it continuously in a loop, until it returns null, it is just printing the di number, which is nothing but this inode number, and it's also printing the name of this directory. Okay, just printing the inode number and the name of this directory. Does this program resemble some other program that we already know? LS, exactly. So this is just like a special type of the LS program. Inside the current directory, if we run this particular program called read dir currently, it's going to read the contents of the particular directory and just go on, just going to loop over those contents and print it. But additionally here, we are going to print it along with the inode number. And so this see here, this program just prints the contents of this particular directory. As you can just see here, dot is printed, then the double dot. All the names of the files are printed along with the inode numbers for those files. And even with LS, we can actually print the inode number by giving like the option I. If you give the option I in LS, it also prints the inode number for each and every file here. Okay? It's very similar to LS. And whenever we open a file, like in this case, when we say we want to open this particular file called /foo/a.txt, then in this case, it is first going to access this directory root. Okay, root, first it's going to access the root, this is called the root directory, it's going to access the root directory and then find out this inode number corresponding to foo, so it's going to then access the directory foo and then it's going to access the file a.txt. So these are the three things that will be accessed when you want to like open this particular file. If this is absolute path name, if it is a relative path name, it's directly going to just access the inode of that particular file, okay, directly. Okay. So the last thing in this file system APIs is about links. Okay, we are going to like see two types of links. Most of you may be familiar with this already. If you are not, this may be interesting. So there are two types of links that are present in file systems called hard links and soft links. Okay, or in other words, this is also called symbolic links. Okay. So whenever we create a file, let's assume we create a file called file1. In that case, if these are the contents of that particular file, let's assume this A, B, C, D, E, these are the contents of the particular file. The name of this file is just like a link to this file. This is the important thing here. So the name of this file, file1, is just like a link. You can think of it like a pointer and a pointee. Like a pointer is pointing to some object. And so this is like a link to this particular file. And so at this time we can actually, if we do something like, first we are going to discuss about hard links. So if we say the command for creating a link is ln, and if we say ln file1, I'm going to create a link for this file called file1, and the name of the link is, let's assume it's called file2. Okay, this is the command that we run. Then what it's going to do is it's going to create something called file2, which is another link to the same file. Basically, they are actually pointing to the same file internally, but they are just two separate ways that you can access this file. And so, in other words, what happens here is, in this particular directory structure, let's assume if file1 and file2 are in some directory, in that particular directory structure, from the human name to that inode number, it's both of these things are just going to, like the file1 and file2 are going to have the same inode number. So both are just pointing to the same file, basically. So if this is the case, and what do you think will happen if we remove file1 currently? Okay, that's what we're going to see now. Just think about what may happen if we remove file1. First, we'll just remove this file. Let's create this file initially. Okay, now I have this file. If we do a stat on this file, file 1, I see that the number of links is 1. So this just says that there's only one link for this particular file. And now if I say link file 1 and file 2, so now file 2, let's see this. There are two things, file 1 and file 2. Now if we open file 2, it's going to have the same contents as file 1. You can see file 1 also. File 1 and file 2 has the same contents. And if we remove file 1 now, or even before that, let's do a stat, okay? So now you can see the number of links has increased from 1 to 2. So we have just created one more link for the same file. And so now if we remove file 1,
Stat file 2 basically say the same thing.
pardon?
So the stat file 2 also.
Exactly, we can do that also. So stat file 2 will also show the same thing. You can check this inode number here. Okay, the inode number that we have here for file 1 and file 2 are exactly the same. So both these two, file 1 and file 2, are actually pointing to the same file internally. So now if we remove file 1, what do you think will happen if we do a cat of file 2? File is still going to exist. See here, the file is still going to exist because we just unlinked one of the links from that particular file. All we did was, if we do a stat of file 2, it just says the number of links is 1. But if you do a stat of file 1, it will say no such file or directory because you just removed this link from the directory entry here. Does it make sense? Just remove this link or with the name file 1 from this directory entry. So it says no such file or directory. And finally, when we remove file 2, okay, this is the time. You just add a single link, and this is the time when the number of links for this particular file goes to 0, and only when the number of links for any file goes to 0, then it's only then that file will be removed from the operating system, so from the file system. File system actually removes the file when the link for that particular file goes to 0. So now if we do stat file 1 or file 2, you cannot find that particular file, it is gone. One important thing to note here is this hard link, okay? We cannot create hard links for a directory. Hard links can only be created for files. Any idea like why this is being prohibited? Why have they prohibited from creating hard links for directories? The reason for prohibiting hard links for directory is usually directory structures are like this. Let's say A, B, and C, D. And now if this becomes like a hard link for, let's say, another directory called D, C is a hard link for another directory called D, then it creates some cycles within the directory structure, and we really don't want to have any cycles in the directory structure, and this is the reason why hard links are not available. Like we cannot create hard links for directories basically. But if you want to do something for directories, then we have something called soft links. Or symbolic links. Here, let's just see the way we create soft links. First, let's again create a file called file1. If you want to create a soft link for this file, then you do something like ln with this option of -s and say file1 and let's say soft. The soft is just the name of the soft link, or this can also be just file2 as we just previously had, okay? So now file2 is a soft link for this particular file called file1. Now let's see what is happening. with a stat. With a stat. So do you notice this? When we did hard link, the number of links for that particular file increased from 1 to 2. But when we do a soft link, the links for that particular file still remains the same. The links is just 1, still 1. Okay? And it says like file 1 is the regular file. So creating a soft link really does not increase the number of links for a particular file. Then let's see like why do we need soft links? So here if you do a stat of file 2, so the important things to notice here is like till now we just told like the file system only has like two types of files. One is called a regular file, another is called a directory. But actually we also have a third kind of file, and this third type of file is the symbolic link. Symbolic link is a special type of file, and here if you see the type of this file is given as symbolic link for file 2 that we just created, and you can notice that the inode number for this particular symbolic link is different than the inode number that we have for file 1. But with hard links, both were the same. Both links were just pointing, both file 1 and file 2 are pointing to the same inode number. But here it is actually different. This ends in 416 and this is like something different, like 150. So now what shall we do is, but if you try printing the contents of file 1 and file 2, it's actually the same. So file 1 and file 2 is actually having the same contents, but file 2 here is a soft link. So what does it mean? Let's see that, okay. But one more interesting thing to note here is when we did a stat of file 1, the contents of the size of the file 1 was 4, okay. Size of the file 1 was 4, which just had like A, B, C with that new line character at the end. But the size of the soft link that you can see here is actually not the same. It is 5, okay. And let's see if you can figure out the reason. Let's maybe create one more soft link. Or first let's try deleting this particular file 1, okay. Now when we delete the particular actual file, the file 1, then what just happened internally is like we have actually deleted the file, but still the soft link remains to this file. So do you think if we do a cat of file 2, will we be able to see the contents of the file? It says no such file or directory, and the reason is, so usually it just says, so this says file 2 is a symbolic link to file 1, but file 1 is actually not present, okay. This is like a dangling pointer is pointing to something, but it is actually that contents is not available. So now I move file 2. Touch just creates a file, so just say file 1, or you can do like something like echo also. Yeah. So I'm again doing the same symbolic link creation, file 1, okay. But this time, okay, this time I'm not going to give just the relative path name. What I'm going to give is the absolute path name. For this particular file, I'm going to create this soft link called soft. And now let's do ls and lrt. So here you can see that soft is like a soft link to this particular file, okay, to this particular file. I think I gave it to a directory, okay. So I did not actually write the file name at the end. So this soft is just a soft link to a directory. So soft links to directories are possible. I was not trying to. remove that soft. So now I created it to that file. Now you can see this soft link to this file 1. But what I wanted to show was the stat of this the soft link now. Okay. You can see that the size is 55. Size of this particular soft link is 55, but initially when we just did with the relative path name, the size was just 5. When we just did ln-s file 2 and file 1. Can you guess like what may be the contents of a soft link? Any ideas? But what may be the contents of a soft link? To say like the same soft link has like a size 5 here, but there it has some bigger size.
Like a string of the address, maybe?
Pardon?
A string of the address?
It's just the count of the characters, number of the characters we have in that particular file that we are creating the soft link for. So I'll try doing this here one more time. So in this case, so here it says this soft is pointing to this entire file, right, with the absolute path name, and so this entire path name is the size of this soft link, because that is the only contents that we have inside that soft link. If I do if I create one more soft link, let's say for this file 1, but let's say it's soft 2, but I just do a relative path name here with the file name as file 1, and now if you do a stat of soft 2, it just has 5 again, because file 1 only has 5 characters in it. Just the size of this particular thing. And even this, if you remember the thing that we use here, the CS 537-2 for the projects and stuff, this is actually a soft link. This particular thing is a soft link to a directory, and the actual directory is like p/co/537/. So what is happening here with respect to soft links is we are not just adding an additional link, we are creating a new file. So let's assume if this is the file, okay, if this is the file with the contents A, B, C, and if this was the name of the file, this was the name of the file, file 1, this is the actual link to this file, okay? But when we do a soft link, like soft, we actually create a new file. This is like, the whole thing is like a new file, but this file, the contents of this file is just file 1. If the command that was given was ln-s file 1 soft, this was the command that was given, then the contents of this file is file 1, which is actually a link to this particular thing, but it is not a hard link. So based on that, it will not increase the number of links for that particular file. And so if you just delete this particular file, when you do a cat of soft, it will go and try to find file 1 for you, but file 1 will not even be in the file system, and so it will just say no such file or directory. That's all it is.
So why do we have both types of hard and soft? Like, is there an advantage of one over the other, or?
So the reason I think they have the soft links is mainly for creating links to directories. Because if you want to create links to directories, which is actually very useful, then you can't create hard links, which increases the link count. But this does not increase the link count, but you can just use that to directly access that particular directory.
Is that just for safety?
Exactly. So if there is a loop, then programs like ls, if you want to like do something recursively, like read a particular contents and then go inside the directory continuously, then it may be in loop forever, just to avoid that.
Can you use, if you create a soft link for a file, can you use that soft link to edit the file? Like you put it in like bin or Emacs, like are you
Exactly. So when you use a soft link to edit a file, it actually edits the actual file. But the idea here is like if you remove the soft link, it's not a problem. But if you remove the actual file, then the soft link is of no use.
Shortcut.
Yeah, it's just like a shortcut. And one more thing when you just told about the shortcut. So we just discussed like we don't have this particular remove directory. Remove directory cannot remove directories which have some contents inside it, but we can remove something like using like remove -rf, and you can do something like the file, the directory name here. This f is just for the force remove. So if you do something like this, then it's just going to remove your root directory. And this is like a very powerful command, and if it removes your root directory, then the file system is gone and you will not be able to access your computer after that. So just be careful and just think like if you want to like crash someone's computer, giving some alias like ls with this thing on the bash rc, if they just type ls, then it's going to like remove the entire thing. So be careful with powerful commands like this, okay? And just also, yeah, you should not do this with anyone, but again, it's just like some tricks that you can play.
What was the R, would you say the RF again, is that?
So RF just says, okay, remove -r just stands for recursive. Recursively remove all the contents of that particular directory, and F is like forceful remove, which says like don't bother if there are any files or not inside that, just remove it like by force. And then final thing, and also, yeah, this just says like remove the root directory, so the entire file system will be gone.
I mean, I'm assuming there's like, is there like security around like people have certain permissions on the root directory, or like I'm assuming like I can't log in to like the CS network and execute that.
Yeah, they will have like things, but yeah, but I'm just saying for your own computers, yeah. I think now we can move into, with this we are done with the file system APIs, now we're going to move into this file system implementation. It's much more interesting. So at a very high level, the idea here is, okay, we are using a device called disk, and some piece of software needs to know like how to communicate with the disk to make sure that when we are writing a new file, and once we close that particular file, it gets persisted on the disk. And for this, we are going to look at the implementation, like how file systems are actually implemented. So let's assume we have this is our disk, okay, and it has 0, 2, so this is the view of the disk from the operating system. So each of this box that we have here is just one block, okay? Whatever we have here is the file system views the disk as an array of blocks. This is how the file system views the disk. And so here we have like 64 blocks. This is like the file system that we are going to discuss. According to the book, it is called the very simple file system. You can think we're going to discuss file system, or very simple file system. And here, as we just saw, like one, so each block of size 4 KB. Okay. And as we already saw when we were discussing disks, one sector is 512 bytes. Okay. One sector is 512 bytes. So what is the size of the hard disk that we are talking about here? What is the total size of the hard disk? Size of the hard disk that we are talking here is, that we are having here is, there are 64 blocks and each block is just of size 4 KB. So the total size that we have here is just 2 to the power of 6 times 2 to the power of 2 KB. I think it's just 256 KB. A very small hard disk, okay? The entire hard disk has just a size of 256 KB, and each block, okay, when we are talking about a single block here, how many sectors are there in each block? So since one sector is 512 bytes, 1 KB has 2 512 bytes, and so we have 4 KB, and so we have 8 sectors in each block. Each block we just have 8 sectors. Now we are just going to answer like 4 to 5 questions to understand how this file system, is actually implemented. The first question is, how to store the user's data? This is the first thing. So whenever there is a disk, we need to store the user data in some way on that particular disk. Okay. So the first thing that we're going to see here is how can we actually store users' data? And the answer to this particular question is we are going to store these in these blocks. Okay. But we have like some special, like some particular type of blocks called the data blocks. We are going to have like things called data blocks to actually store the contents of the user's data. So here by contents we mean if we are creating a file and if we have like 1000 bytes in that particular file, all those 1000 bytes are going to be somewhere on the hard disk. And in this particular example, let's assume, okay, let's assume the blocks from 8, okay, like all these blocks till 63, these are the blocks for users' data, or in other words, these are the data blocks. We will find out like why are we like, usually the file system reserves some space in the front, okay, for some bookkeeping purposes. Okay. And so the first thing that we need is like, okay, we need some blocks for actually storing the user's content of the files, the user's data. So we have the data blocks. The second question that we want to answer is, okay, once we have the user's data, okay, data are stored somewhere. So let's assume there are like some 3 files or something like that in this particular file system on this hard disk. We need some way to understand which data blocks belong to which file, right? We need some organization to understand, okay, these are the data blocks that belong to file 1 and the other 3 are the data blocks that belong to file 2 and some organization like that. And so how to store file metadata? Metadata is nothing but data about the data. So here, these are the bookkeeping structures that we are going to store for these files, okay, for these data blocks. And let's just talk about some of the metadata that we already saw. So what are some of the metadata that are associated with a particular file? If you have a file, data, these are the data blocks, okay? But we just saw whenever we did a stat, just think about what are the different things that we saw in a stat. I'm just going to list them down here. So one particular thing, if you remember the type of the file, right? The type of some file, either is it a regular file or a directory or a symbolic link, the type should be stored somewhere. Let's assume, okay, this structure that I'm drawing here is just a metadata for a single file, okay? For a single file on this file system. And so, and then we have the size of the file, remember. You remember any other important things that we saw? What? Links, exactly. We have the number of links in each file. We also had a field like the number of blocks, if you remember. But we did not go into that. But here, just means like how many blocks are allocated for that particular file, or how many blocks are in use for that particular file. And there are also information like access time, the owner of the file, and a bunch of other things, okay? A bunch of other things. But the most important things comes like after these things, okay? After these information, the metadata that we have here is called like the logical, this is like the logical block 0. This is the logical block 1, logical block 2, and in this example, in this file system, let's assume we have till logical block 14. We have, let's assume we have like 15 logical blocks for each file. Okay. If this is the case, what is this logical block? This logical block is just a pointer to the actual data block. It just has the number of the data block. So you may think of this logical blocks. So for this may point to, let's say, data block 7. This can point to, if the file has, let's say, 3 data blocks, this can point to data block 21, and this can point to data block 3. So the important idea here is, from the perspective of this metadata that we are having, there are these logical blocks, logical block 0, 1, and 2. And so the initial contents of this file, the first, let's assume there are 3 blocks, first 1/3 contents of these files are actually stored in data block 7. So just to correspond to these numbers that we have here, like to the block numbers that we have, 8, 9, 10, just changing these things, okay? Assume this to be 9, this to be 21, and this to be like 30, okay? So here we are just saying this particular block, the data that is inside this particular block at 9 is the first logical block for this particular file, okay? And so these are the different informations that we are having. And the important idea here is like the logical blocks will be in sequence because the file contents are sequential, but the data that is being stored in the blocks need not be sequential. So these 3 blocks are actually scattered somewhere. But as much as possible, the file system tries to store the data for a single file like sequentially. Even though I've just shown like 9, 21, and 30, if it was possible, the file system would have stored it at like 9, 10, and 11 if those 3 blocks are free. And you think why? Why that may be the reason? Pardon? Exactly. So it's again just because sequential reads or sequential writes are much faster than random reads and random writes. So this storing the blocks sequentially just reduces the access time for these blocks. That's the reason. Usually it is done sequentially, but if it's not possible, those can be scattered somewhere on the disk. Those information are here on this logical blocks.
Question. So are the data blocks, are those represented on the disk?
Yeah.
And then the metadata, is that also on the disk, or is that like still up in the operating system?
Yeah, that's a very good question. So the question is like the structure that we are writing here, okay, is it on the disk or is it on the operating system? Actually, it will be both on the disk and on the operating system. So here, this structure that we are talking here, okay, it is actually how to store the perfect metadata is using a structure called inode. And whatever we just discussed right now, the entire structure is actually called an inode. And each file has its own inode. Okay? This whole thing is called inode. And so, if we want to maintain this information for each and every file, okay, then we need to make sure that we need some space here for these inodes, right? Let's assume in this file system, let's assume the blocks 3 to 7 are for storing the inodes of the files. Okay? And usually the inodes, size of the inodes, usually like 128 bytes or 256 bytes. For this example that we are seeing, let's assume we have inodes of size 256 bytes. Each inode structure is of size 256 bytes. So if this is 256 bytes, and each block is just like 4 KB, can you calculate how many total files can be on this file system, on this particular file system that we are seeing here, the very simple file system? Given these parameters, we have only 5 blocks in total for storing the inodes, and each inode is of size 256 bytes, and multiple inodes can be grouped together in a single block. Okay, in a single block, multiple inodes can be grouped together. Can we calculate the maximum number of files that can be created on this particular file system? And that includes files and directories basically, because directory is also a special type of file and it also needs an inode. Anyone? Exactly. So I think it's 80. So to check that, okay, we just have 5 right here, max number of files on this file system. This we have 5 so maybe 1 second, let's just do like in one inode, okay? So in one block, how many inodes can we save? This is of size 4 KB, and we can actually save, since each is of size 256, this is 2 to the power of 12 by 2 to the power of 8 to the power of 4, 16. So in one block, you can just store 16 inodes. So one block can contain 16 inodes, and I'll just write it down here. One block can contain 16 inodes. And so we have 5 blocks that are reserved for the inodes in this file system. So we can have 80 inodes. 16 times 5, we can just have 80 inodes in this file. And so this corresponds to the maximum number of files that we can have. This place that we can only have maximum of 80 files in this particular file system. In the same way, using the inode structure that we have here, can we try figuring out what can be the maximum size of a single file? What can be the maximum size of a single file in this file system? How many bytes can a single file be? So the idea here is like we only have, this structure is fixed, okay? This structure is fixed, but so we only have 15 logical blocks for each file. And so each block, each logical block maps to one data block, corresponds to one data block, and one data block is of size 4 KB. And so the maximum size of a file in this file system, max file size is 15 times each block, one block size, which is 60 KB. So we can only have like a 60 KB worth of data in a single file.
Is that why file systems like NFS limit you how big files can get?
No,
No.
this is like, again, here we are just talking about unrealistically small file sizes, okay? But actually, the idea in real file systems will be, again, I'm just going to draw this inode structure just to show like how this will be actually implemented. So let's assume we have all the metadata here. Okay, all the other things that we have here, and these are the logical blocks. Logical block 0, block 1, the last one, okay? If usually what happens is like the 15th logical block in this particular case, because the problem here is like if this is the maximum size of a single file, then it's like too small. So how can we increase the maximum size? The idea here is we have these logical blocks. This last logical block, these point to data blocks directly. Let's assume this is data block, this is another data block. Okay? But this last logical block will be pointing to a data block. It will still be pointing to a data block. Okay? This is again a data block. But what we will be doing with this data block is we will just use this, split this up, and use this as like pointers to other data blocks. Does it make sense? So this logical block that we have at the end, this last logical block, is called an indirect block. Like a double, this is called a double indirect block. So it means you come here, you go here, and then this particular, there will be data blocks address here, okay? And the actual data block will be residing somewhere. And so now we will be pointing to multiple data blocks from this logical block. So let's assume, in this case, just to understand like what may be the file size in this case, okay? Let's assume each of this, you need just 4 bytes to store a pointer to a data block, okay? Let's assume we need just 4 bytes to store a particular pointer to a data block. If this is the case, what is the file size, maximum file size in this particular case with a single double indirect block? And the logical block 0 to 13 just point to single data block directly, but just the last logical block points to another data block, but the contents of the data block are organized in a way such that each of it is pointers to other data blocks in turn. And so, can you try like what maybe? So the idea here is again just to see how many pointers can be stored here. So the number of pointers in indirect block, let's call that the indirect block. Size is 4 KB by 4. You can say like one. Am I doing it right? You can just save like 1 KB size of pointers. So 1024 pointers can be stored here. So in turn, we have increased the file size by 1024 times 4 KB. Does it make sense? So now the maximum file size in this case, max file size is going to be here. Right now we don't have 15 logical blocks, but in turn we only have 14. Okay, directly we have 14. So 14 times 4 KB plus we have 1024 times 4 KB. So this is nothing but 4 MB. So file size has increased by 4 MB minus 4 KB.
So the number of blocks in the metadata, like, tells us how far to search down.
Can you please repeat the question? So are you
In
asking?
metadata, there's a number of blocks in that file, right? And that tells us how many blocks it is searching the data. We wouldn't go double track block by data once we use that.
Exactly, yeah. So the question was, we have this information like the number of blocks. We will be actually using that number of blocks to make sure that if the number of blocks in this file was just 3, then it means that only the logical blocks 0, 1 and 2 are used. And we will not be even going down the path for accessing any of the other things because this file just contains 3 logical blocks, 3 like data blocks. But these things would happen if it's a very large file. Okay, that is the case when it would be going in this way. One more interesting thing is like in real world file systems like ext2, ext3, current Linux file systems ext4, we actually have one more layer of indirection more than whatever we have just seen here with the triple indirect pointer. So this is like a double indirect pointer. So similarly, we will have like a triple indirect pointer. So just the idea is, I can just show here. Okay. So this thing in turn will actually point to a data block, which in turn will point to other data blocks, which are also still pointers, which in turn will point to the data block. This is like a triple indirection. So here again you can easily see these may contain 1024 addresses, and each of the thing that this is pointing to, the second thing let's assume, each of the thing that this is pointing to will in turn contain 1024 addresses, and then the file size now will increase from, it will again have 14 times 14 times 4 KB, then it's going to have 1024 times 4 KB. Does it make sense? So with triple indirection, the file size, the max file size that we can have is 14 times 4 KB plus we have 1024 indirect pointers here. So 1024 times we have each of these 1024 actually points to data blocks of pointers again. So we have one more 1024. Each of those things point to data blocks, which is 4 KB of size. So this becomes actually 4 MB and 4 GB. So it's approximately 4 GB. So the total file size, maximum file size in real world file systems is around this size. Okay, with the triple indirect pointer.
Did you say that the number of blocks, like the metadata, the number of blocks, is that how many data blocks it is, or is it, so like if you're using some of the blocks that are in the pointer, it reflects that number?
Yeah, so the idea with the number of blocks is like all these things will only be used sequentially. In turn, they are very similar to these logical blocks. Even in this indirect block, each of these things will be used only sequentially. Sequentially, I mean like it will be filling up the logical blocks only in sequence. So then only then it can understand which part of the data blocks belongs to which part of the file. So the initial contents of the file is always going to be in logical block 0. Okay, and the next, so that means the first 4 KB of the file is always in logical block 0, wherever that data block is. And second 4 KB will be in the second data block. There will not be any gaps here. The file size increases, it's going to use like, okay, first pointer here, then second, then it keeps on going in that way. Any questions with this? Okay, now let's see how can, when the file system says, okay, when the file system says read block 8, okay. If the file system just says like read block 8, then what is the actual sector number that this is going to be converted to in the file, in the actual disk? What is the sector number that this is going to be converted to? So we just know like each blocks are of size 4 KB. So it's going to be 8 times 4 KB is the total number of, is in bytes. We are going to access that particular thing, which is 32 KB. So here if you see by block 8, we are saying this block, okay. But what does the sector number for this block correspond to is the question. And so if you want to like convert this to sector, so here you are just going to say sector number is nothing but 32 KB by size of the single sector, which is nothing but 512 bytes, right? So this is 2 to the power of 5, 2 to the power of 15 by 2 to the power of 9, 2 to the power of 6. So 64 is the sector number. 64 is the sector number for this particular block. Okay, because the file system only issues reads or writes in terms of blocks. In turn, the disk has to convert it to the actual sector number to make sure that we are writing in the correct sector. In a similar way, can we figure out what is the, if the file system says read the inode number 32. The file system says read inode number 32. Can we map this to the actual sector number that is going to be read? It may take like a minute to see if you can figure this out. Again, remember, we are using this particular thing, okay? So file system just says there are like a lot of inodes. We know like there are 80 inodes now, but the file system just says read inode number 32. Can you map this? As we can just say there will be 16 inodes in each of these things, right? So inode number 32 is the inode that is here. Remember 0 to 15 will be here. Then 16 to 31 is going to be here. So inode number 32 is the first inode in block 5. If you can figure that out, then it's just going to be in a similar way. So we can actually figure this like what is the address of block 5. You can figure out the address of block 5 in bytes and then divide it by the number of sectors. Then that is going to give you the sector number for this particular inode. Try doing this. So one way that we can do this is we can just calculate the offset, okay, from the start of the inode. If you want to calculate the offset from the start of the inode, it's going to be, we are about 32nd inode, and each inode is of size 256 bytes. So this is 2 to the power of 5 times 2 to the power of 8, which is 8 KB. Okay, it's 8 KB. Okay, it's just 8 KB from the start of inodes. Start of inodes is here. Okay, so what is the actual start of this particular location is, we can think like this is 0, this is 4 kb, this is 8 kb, and this is 12 kb. So we need to add 12 kb to this particular thing to calculate the start address of this inode. Start from let's say the beginning of the disk. Okay. This is going to be 12 kb is what is reserved for some other things which we haven't seen yet. So we have 12 kb plus this 8 kb, which is the offset within this inode from the start of this inode. Okay. So it's just going to be 20 kb. 20 kb is the address that we are that we want to access for accessing the inode number 32. But with respect to sectors, if you want to calculate the sector number, it's just going to be this whole thing 20 kb divided by a size of sector, which is 2 to the power of 9, which is 20 times 2 to the power of 10 by 2 to the power of 9, which is 40. So 40 is the sector number.
If you want to find the sector number, since we know it's in we know that it's starting in block 5 and there's 8 sectors in every block, just multiply it.
Yeah, you can also use the same way, but this would be like the idea of finding out it from the beginning of the thing would be useful for some inodes in between, somewhere in between the block. Because this starts at the beginning of this, directly you can use the previous method that we just did. Again, yeah, this is a roundabout way to do this because we already know that we have here, but I just wanted to show this to find some sector number like 37 or something like that. Some inode number like 37, something like that, which may not be straightforward. Okay, I think we can take a small break now. And once we saw how to store perfect metadata, then till now we did not see how to store directories in this particular file system. Do we need any special like structures for storing directories, or do we have everything that we need to store directories already in this? So as we just told, directory is just a special type of file.
Well, no, you're actually, so you do your access 0, access 1.
Exactly, so we really don't need any special type of metadata, or special structure of metadata for storing directories, because directories again are considered as just special type of files, and each file needs an inode. We have an inode, just we will be using this type here to make sure that it is a directory. When you do the ls command, if you see the leftmost column, if it's a directory it will be D, and if it's just a normal file it will be just like a dash. And we can use this type field here in the inode to specify it's a directory, but the contents, as we just saw already, okay, for the contents of the directory are just going to be that mapping between the human readable name and the inode number. So the contents are going to be like in some special format designed by the operating system. So for directories, how do we use directories? We are going to reuse inodes. Just change the type of the inode to be D for directory. And then in the data blocks, okay, let's assume in a particular data block, and if this data block contains the data of a directory, this contains, let's say, data of directory, then it will not be just some random bytes, but it will be like in this specific format. As we already saw, it's going to be in this human readable name and in this inode number. So now we can easily relate to this. That will be like some numbers. Some contents will be like this in this particular thing, and so that is the reason why we as users cannot directly write to a directory. cannot perform a write to any directories. The next thing to discuss is, with all these things, what are the other extra information do you think we need? So let's think about the case when a new file is created. Okay, when a new file is created, we need some structures to understand which inodes in this inode list is actually free, right? We need some structures to understand what are the inodes that are free. And after creating that file, when that file is, when we are going to do some write to some data blocks, we also need to understand which of the data blocks that are available from 8 to 63, which of those are free, okay? So the fourth question that we are going to tackle is how to track free inodes and data blocks. How to track the free inodes and data blocks. So file system, in this case we are going to use these two things, okay? And one particular thing is for the inode bitmap. Called the inode bitmap, okay? And this is called the data bitmap. We allocate like a whole block, but even though with the bitmap, we are just going to use an inode bitmap. It's going to be like this. Inode bitmap is just like an array of bits. It just has, we have 80, we can have 80 inodes in this particular file system, right? So it's going to have from 0 to 79. And if this is like 1, 0, 1, 0, it means like inode 0 is allocated, inode 1 is free, inode 2 is allocated. Like this is allocated, and this is free. In a similar way, we need a bitmap for, but the idea here is like this just occupies 80 bits or 10 bytes in total, okay? The size of this inode bitmap is just 10 bytes. Even though it's just 10 bytes in the simple file system, we will be actually using that entire block for the inode bitmap. Okay, the remaining space is wasted. Similarly, for a data bitmap in this file system, how many data blocks we have in this file system? We have 64, but we are not using these initial 8. So we have 56 data blocks in this file system. So the data bitmap is going to run from 0 to 55. And similarly, it's going to have some like bit pattern here, using which we can figure out which are the data blocks that are free and which are the data blocks that are not free. On top of this, do we need anything more? We have structures to track files with the blocks of data blocks of a file, which are the inodes. We also have structures to track which are the free inodes, which are the free data blocks. Do we need anything more? I guess just like still we have one space left, so we're probably going to need something. So one more, the last structure that we actually need is to figure out, okay, if there is, like how many inodes are there in this particular, how many inodes are there, how many data blocks are there, what is the total size of this file system. All these details need to be stored somewhere, okay, and so that is stored in a file, in a thing called the super block. This is called super block, and super block is the first block that we have in this file system, and it stores details like how many inodes, it says like 80 inodes are there, and how many data blocks are there, 56 data blocks are there, what is the total size of the file system. It is 64 times 4 KB that we just saw, right, 256 KB. And using this, whenever a file system loads data from the disk, sanity checks would be made just to make sure that the amount of free space that we have on the disk is less than the total size of the file system and things like that. And using like those sanity checks, we can be sure that this super block or I mean this file system is like a correct file system, or like nothing has been like modified or no one has tampered this file system in any way. Okay? This, and it also is used to figure out like, okay, where to the inode star, the superblock has like details of the structure of this particular file. So with this, now last part of this class. We're going to just discuss about access methods. So the idea here is, now let's just think about if we want to read some data from a file called, just have it like slash foo slash bar.txt. This is the file name and this is like a directory, and if you want to like read some data, if the operation is read, if you want to do a read, what are the different structures that we are going to access? This is called access, this part is called access methods. What are the different structures that we need to access to actually read the data of this particular file? Okay? You can assume as of now that all the structures are available or just on the disk. Okay? If all the structures are on the disk, then how will we access the data of this particular file? So maybe let's do something like so first let's just think like for reading a particular file, do we need to access the data bitmap or any bitmaps, data or the inode bitmap? Do we need to access data or the inode bitmap for doing a read? Or the first thing, okay, so usually let's come to that later. Let's see if we need to access the data bitmap or the inode bitmap. The first thing that we need to read is the inode of the root directory. Is that right? Because only if we read the inode of the root directory, we will be able to go and access the data blocks of the root directory. And using the data block of the root directory, we will be able to find out the inode of the particular folder called foo. Okay? So here we are going to read the inode of root. Okay? Second step is going to be, we are going to read the data block of root. So this gives us the table kind of structure with the human readable name and the inode number or the I number, and using which inside this will be an entry will have like foo with some inode number, right? And so now using this particular data, you will go and read the inode of foo, this directory. Because we have this inode number, we can directly go and access the inode of foo. And once you access the inode of foo, you also have to read the contents of that particular directory foo. So you have to read the data of foo. And foo's data will be something like, will have this file called, it will initially have you have this file called bar.txt with some inode number. So you got this data now, and now you have this inode number. So now you know you have to just go and read the inode of bar.txt And when you go to read the inode of bar.txt, you have those metadata there, and using the logical blocks, now you can actually go and read the actual data. So let's assume this bar.txt currently just has 2 blocks, okay? 2 data blocks. It just has 2 data blocks. For simplicity, we can just assume 1 data block. So here you're just going to go and after this read, after this read of the inode of bar.txt, we are going to do a read of the data block, first data logical block, data of 0 of bar.txt. This is how we actually read it. But since we just read this file, it is counted as like this file has been accessed. We had read this file, and so you will go and change the, you will go and write to the inode of bar.txt. There are 2 things like modification time. Modification time will not be altered, but since we just read this thing, this was the last access time will be changed here for this particular file. So these are the different structures that are accessed for just doing a single read of bar.txt. Any questions about this? Because the last thing that we are going to see is like what happens on a write. It should be much more interesting, and as you just saw here, on a read, we will never access the bitmaps. You will never access the inode bitmaps or the data bitmaps, because those are structures that are only needed when we are going to create new, like when we want to create new files or write some data into some already existing file, which needs like new data blocks. So the last thing that we'll see is what happens on the assumption is we are going to create this particular file, create this particular file, and then just write a data block to this particular file, create and write a data block to this particular file for this. So now we need, so the inode bitmap, and this is, you can say this is a data bitmap, inode bitmap, a data bitmap, and then there is this root inode, then the fuse inode, and the bar.txt is inode. Similarly, you have the root data, fuse data. Bar can have a lot of data. As of now, we can just assume there's only one data block that we are going to write. And so we assume that time runs from top to down. Time runs from top to down. So for the first thing, we are going to do a create, let's say /foo/ bar.txt. What is the first, again assuming none of these structures are in memory, what is the first structure that we are going to read or write to? The first structure that we are going to again read is the root inode, because we want to find out where that file actually exists. So the first thing that we are going to read is the root inode. And as we saw previously, after reading the root inode, we want to read the data inside the particular directory to find out the inode number for the directory called foo. And so you go and read, we can draw lines here. So the second thing that's going to happen is reading the root data. After reading the root data, you want to read the inode, you would have found out the inode of foo from this roots data, and so you would want to like read this particular thing, foo's inode. After reading foo's inode, we are going to go and read foo's data. Okay, now are the interesting things. So now when we read foo's data, okay, we have some directory structure which does not have this file in it. Okay, which does not have this file in it. So what is the next structure that is going to be accessed in this case to create this file?
Is reading that just to check the file exists?
Exactly, yeah. Just reading that as a check if the file exists, and also for making sure that we want to like write or update that particular directory data, right? Because once we create this file, we are going to like update that particular directory data. So now, after we read this foo's data, we have got the directory structure, but we don't have that file in it. So for creating this file, now we need to access which structure? The inode bitmap. We want to create this new file. So first we want to figure out what is some inode that is free. So you have to read this inode bitmap. So read this inode bitmap, and immediately after figuring out which one is free, select some particular inode from there. So you will be like writing to this inode bitmap, okay? This read and write happens. And each line is just like a step, okay? Like time proceeds like this. The time proceeds downwards. And then after finding out a particular free inode in the list of inodes, now we have to update the foo's data with that particular entry. Does it make sense? We need to update the foo's data with the entry with the human readable name saying bar.txt and with the inode number that we just chose from this inode bitmap. And so we are going to do a write here. Okay? And after we do this right, what are we going to do? We are going to, now we know the bars inode because we just got one from here and we wrote the contents inside this foo's data. We just read that bars inode. And now that is a particular location on the disk. So we are just reading contents from that particular location just to update that. Now we want to update that inode with the contents of the, let's assume we are creating this particular file, right? So now when this file is created, we want to like update this file's inode with the initial things like number of links, the owner of the file, file creation time, and all these metadata in that particular file. So we are reading from that, let's assume it says like inode number 32. We are just reading from that disk location. This read happens from the disk location where that inode number 32 is present.
But why? Like, are we going to overwriting it? Why do we care where it's there?
So the idea here is we are like actually reading that particular thing just to make sure that we have some, what to say, like initial value that we can work with in that particular inode for bar.txt. So,
I mean, is it like security or just making sure it's...
Is it just kind of how a write happens? Is you read it, you change it, and then you write it?
no, so maybe I'm not very sure, but at least when we write data blocks, we really actually don't write, we don't read the data block. If we are writing new data blocks, we just write the data blocks. But whenever we are reading some inode, usually the way it happens is it's just told we read that particular contents and then we modify the particular contents in that particular data block. I can maybe figure out.
Like, what would have been in there since it wasn't allocated before?
Oh, because you have the whole block, right? So you have several inodes in that box, and you read all of that data, so you can change that one inode and then put it back.
Exactly, that's what is happening.
You can't just
Yeah, I think this is the answer. Just I just told. So since inodes are like grouped together as blocks, okay, we can't really just update that particular value inside the block, because if you want to, thanks. If you want to like actually update a single inode, you need to update the entire block. Even though the update goes to that single inode, the update happens to the entire block because the file system only deals in terms of 4 kilobyte blocks. And so that is the reason why we are reading that entire block here to update that particular inode.
So this pulls it off the disk into like memory and you make your update and write it.
Exactly. So this pulls it off from the disk to the memory, and once that block is in memory, now you can update that particular. You can update that particular block with using a write. Okay. And since just we modified the contents of this foo directory using this new entry that we just added for bar.txt, we are also going to update the foo's inode. Okay, we just update the foo's inode because we just added a new entry for bar.txt inside here. We read it already. I think if you see just before that, foo's inode was read at time 3. We have read foo's inode already. Okay, it is in memory, so we just like now write it down.
Is it, what do we, for the foo inode, what is it that we would be updating for? Like, would it just be like an access time or something? Because the actual method would be the data block, right?
Yeah, so since
So what is it on the inode, like that would be updated?
yeah, since we updated this data block, we just modify the latest modification time. That will be updated here. So the actual contents goes into the data block with that particular write, okay, on this right hand side. And this is just like the file modification, latest modification time for this particular directory which is being written here. And then when you want to like write a particular, if you say we are going to write some data, okay, if you want to write some data into this particular file, you are going to read this file's bar.txt's inode, because you need to find out how many data blocks are there in that particular, for that particular file. So you read bar's inode, and so this is still here. We have covered just for creating a file. We needed like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like 10 IO operations. And after this, for actually writing some contents to the file, we read the bar's inode. Then we need to find out, since there are no blocks already, we need to find out one free block. So we read the data block and we update the data block after figuring out which data block that we are going to use. Okay. And then now for writing to the blocks, you can just directly write it, because we don't need like any information from that block. Even though we are updating little amount of data, the size that will be returned will be like in 4 KB blocks. So here we are just going to write in this particular thing. Okay, this particular thing we are going to do a write in this data block, and after doing this write, now you need to, since we just added a new like a data block for this particular inode, you will also write this inode for bar.txt, because the size of this file would have changed now. The size of this file would have changed. And similarly, these 5 IO operations that we see here would be the same if we are writing additional blocks to the same file.
So is that also in that right where we would update the block mapping,
So
right? Because we wrote.
exactly. So that particular the block that we chose got here will also be marked as the first logical block for that particular file here. Okay. Again, these are like not strict orderings, because here this write can even happen like in some different order, and with that caching that we have on the disks, like these writes will be issued to the disks, and the disk cache can in turn decide in which order it wants to send it to the disk, and that really creates a lot of problems, which will be the focus of discussions for the next class.
Yeah, I was just gonna ask, if going back to the two I know read and write, we could assume that it was atomic, so we could just read the clues I know and write it. So rearranging
Yeah.
all in all.
Any questions?
I get, so when we read it, right, we read in that I know block, the first time we read it for Bartek's I know, and then we wrote to it to indicate that, you know, we got this new I know, and then we read it again. Like, do you necessarily have to read it again?
Yeah, because the
or-
contents of that particular thing has changed. Now it is on disk here. Again, in this case, if we have like a cache, disk cache, then that read will not actually go to the disk. It will be serviced from the cache itself. Okay, this is all I have for today. I mean, we thought, and we will be like.